This is an early 20th century military trench, and today we'll be enhancing and optimizing this cinematic scene. This scene is currently available on the Fab Marketplace if you'd like to follow along. We'll be doing an intermediate deep dive on 3 unique features inside of Unreal Engine 5. Landscape blending with Megascans assets using RVTs, procedural scattering with PCG, and we'll take a look at Unreal Insights to help us profile and optimize the scene. Virtual texture support is enabled by default if using 4.6, but if you're on an earlier version, verify it's enabled in the project settings. Let's take a look at this basic landscape material I've created. I have a section for layers, adjustments, a landscape layer blend, and I connect the result to a material attributes output. If you'd like to use material attributes, you can do so by ticking the box in the details panel. Let's take a closer look at the base layer textures material function. The first thing that's important to cover is that in order to use RVTs to blend our landscape with Megascans assets, our landscape material has to reference regular textures instead of virtual textures. This is because there's no feedback pass, so the engine doesn't know which tiles to stream for the SVTs. There's a couple ways to ensure we're using regular textures instead of virtual textures. You can right-click a texture, and if it says convert to regular texture, then select the option. We can also open the texture, search for virtual, and select the convert to regular texture button. Back in the base layer textures material function, let's take a closer look at the height section. I'm using the green channel for my height map to drive the displacement and the height output, which will be used for height blending the landscape layers. With DXT1 compression, the channels are compressed to R5, G6, and B5, which makes up the 16-bit color format. So I like to use the green channel to get a little bit better quality with things like roughness and height maps. One thing to note is that DXT1 compression is very aggressive and prone to artifacts at lower resolutions. If you find those artifacts to be too much, try other compression methods, such as BC7. With better quality compression, you'll see bigger file sizes. However, you may also find you can lower the resolution further on textures while still having better end quality. So it's important to experiment and see what works for your specific needs. Let's take a look at the base layer adjustments material function now. This material function contains most of the material adjustments, including base color, roughness, and height. I've created a material instance from the landscape material, and I just want to get it set up in my scene now. Once the material is assigned to the landscape, I need to go to the landscape mode and then select create layers from assigned material. Now I'll create the weight blended layer info objects that will contain the data generated when I'm painting my layers. You'll notice that my landscape is still black, but that's just because I need to paint some layers to get them to show up. To enable nanite displacement for a landscape, let's jump back into the landscape material and go to the details panel and search nanite. I'll enable tessellation, and under the displacement dropdown, I'll set the center to 0 and so our landscape remains in the correct location. Magnitude controls the intensity of our displacement, which is directly affected by the z-scale of the landscape being set to 100. So I'll keep the magnitude low to compensate for the z-scale. I'm not seeing displacement on my landscape because I still need to enable nanite and build the data. Then we should see displacement take effect. It's a bit hard seeing displacement on this mud, so let's paint a layer of rock and see what it looks like. The rocks are a bit much, so I'm going to jump over to my material instance and dial the displacement down a bit. Now that the landscape material is set up, let's dive into making use of RVTs to blend the landscape with Megascans meshes. We'll need to create 3 RVTs, one for the base color, normal, and roughness, one for displacement, and one for world height. Before we get into editing the materials, we also need to assign each of these RVTs to the landscape. Once added, we can select Create Volumes to generate the volumes which automatically scale to the size of the landscape. Let's jump back into the landscape material and get the material attributes we want to project into our SVTs. To start, let's get our base color, roughness, and the normals. To project these attributes into our SVTs, we'll need to drive them into a runtime virtual texture output node. At this point, we could choose to use our material attributes to avoid using SVTs for the landscape, but in this case I want to sample from the RVT that we set up earlier for base color, roughness, and normals. To do so, I'll search for a set material attributes node, add base color, roughness, and normal, and then connect the pins. Everything is looking okay in the scene, but now we need to add functionality for displacement. Let's do that by adding the displacement output for our Get Material Attributes node, and make sure it's connected to our runtime virtual texture output. Now let's duplicate the RVT sample node and replace the currently assigned RVT with the displacement RVT we created earlier. Let's also add a displacement pin to our set material attributes and connect the second RVT's displacement to the pin we just created. Back in the level, we can see that displacement is working again. I've duplicated the default virtual texture Megascans material and will use this as the source material for assets I want to use RVT blending with. I'll grab a world position node and a RVT sample node to sample the world height. If I subtract the world position and Z from the world height on my RVT sample node, we'll get an evenly split black and white mask. Now I can add to this value to shift the world height up and down, and I can divide the value to blur the transition. I'll add a 1- to invert the value and a saturate node to keep the values between 0 and 1. This is important whenever using a linear interpolate node, since the values outside of that range can produce odd effects. At this point, I'm playing around with values to get a feel for how these parameters will affect assets in the scene. Now I just want to visualize the mask by plugging it into the base color. From here, I can dial in the settings to something that will work for this particular asset. The mask is working well for the asset, so I'm going to set up a named reroute node called alpha that I can call in other parts of the graph. I'm adding a linear interpolate node to blend between the static mesh base color and a value of 1 using the mask we previously created to drive the alpha. With the basic blending setup, it's time to sample RVT base textures and connect the base color, roughness, and normal to their respective linear interpolate nodes. It's a bit hard to see if the blending is working or not, but if I switch to unlit mode, we can see that it is definitely working now. The main reason it's difficult to notice if the blending is working is because we're still getting a hard normal transition from the intersection of the mesh and the landscape. If I go into the world normal view mode, we can see this harsh transition line. Let's fix that. First, we'll need to go back to the landscape material, and let's add a transform node after the RVT sample to convert the normals from world space to tangent space. Similarly, in the material for my Megascans mesh, I need to do the same. Now if we check the world normal view mode, we have this smooth transition between the landscape and the static mesh, just like we want. And playing around with the mesh confirms this is looking much better. It's worth noting the seam will still be somewhat apparent when the mesh faces are perpendicular to the surface of the landscape. I want to upgrade the masking by adding in some edge breakup. A simple way to do this is by using a noise node along with some parameters to control intensity and contrast of the noise. It's worth noting that a noise node can be a little expensive compared to using a texture sampler. Now we can use a height lerp node plugging our previous alpha into the transition phase and the noise mask into the height texture input. When using a noise node, the default min is set to -1, and setting the value to 0 will fix the output balance. From there we can grab the alpha output and direct it into the previously made alpha reroute node. If you've used virtual textures for any amount of time, you've likely run into the resizing virtual texture pools message before. Let's go to the project settings, find the virtual texture pool settings, and discuss how these work. We can set the default size in megabyte to affect all compression types in your scene. If you're in a rush and making a simple cinematic, increasing this value to 512 or 1024 would likely make the resizing pools message go away. If you need more granular control, simply create new fixed pools that have the same compression types as the transient pools. It's best to avoid setting the min and max tile size to the same values as the transient pools, as anytime the tile size shifts, it can trigger new transient pool generation. Instead, you can set them both to 0 to include all tile sizes, or define a range of tile sizes that fit your needs. To check that it worked, delete the transient pools and fly around your scene to ensure transient pools are no longer being generated. Let's go over some additional settings, console commands, and what the feedback those console commands are telling us about our scene. Our VT Residency Show 1 will display some live graphs going over how much memory we're using for each compression type being used in our scene. The red line represents pool occupancy from 0 to 100%. This is the culprit for the resizing pool message. Typically, it gets oversubscribed from small default pool sizes and having a higher resolution output. The green line represents mip-map bias being applied to keep residency below 100%. If fixed pools have enable residency mip-map bias ticked on, and you're becoming oversubscribed on the red line, then this feature will kick in to keep it below 100%. The yellow line represents the fixed pool occupancy. This is a locked value that can become oversubscribed when there's a very large number of loaded virtual texture assets. Back in the project settings, I want to increase the tile size quite a bit to see if I can get better resolution on my textures. This will prompt a required restart of the editor, and after reopening the editor, I'm noticing some glitches and I'm getting the resizing virtual texture pools message again. Our VT Residency Notify 1 notifies you if you're oversubscribed, and I can see that I'm oversubscribed in DXT1 compression. Let's also take a look at our graphs now and compare them to when I had it set to 256. We can see that page residency automatically created temporary pools to keep them in memory, and what we're actually oversubscribed on is DXT1 in the locked page residency. I'll need to reduce the amount of virtual texture assets in my scene to get that back in memory. Stat virtual texturing can be a helpful set of diagnostic statistics that can help inform how SVTs are being used in your scene. Lastly, VT borders is a useful way to visualize the tiles being generated for your assets. Before moving to the next section, I also want to bring awareness to our world position node in the RVT Megascans material. It's generally best to utilize camera relative world position as you'll have consistently higher precision near the camera, and it's more optimized especially for large scenes or open worlds. If you'd like to learn more about this, there's a great write-up on the Unreal Engine forums that does a deep dive on this topic. In this part of the tutorial, we'll create 3 PCG setups that can prove useful when making environments. Let's start by enabling the Procedural Content Generation Framework and the geometry script interop plugins. And now let's create an empty PCG graph. In that graph, let's grab a getActorData node. This node is very useful for communicating with actors in your scene, and in this case, we want it to communicate with itself. Let's also set the mode to single point. I'll add a projection node with the landscape data plugged into the projection target. If you want to project points on top of other static meshes, use the world ray hit query and be sure to generate collision for your static meshes. Let's add a debug node, set the scale method to absolute, and size down the scale so we can visualize our point behavior. That looks right, so let's spawn a static mesh in place of this single point by adding a static mesh spawner and adding our mesh entry. And it looks like a problem has occurred where when I scale the volume non-uniformly, the box is scaled as well. I'd like the box to remain the same size regardless of the scale of the volume, so let's fix that by adding a transform points node and enabling absolute scale. Now, however I scale the volume, the mesh remains the same size. We have the basics set up, but how do we spawn a level instance through PCG? It's pretty simple. We just go to our level instance, right-click, and under Asset Actions, we can select Create PCG Assets from Level. From there, we can drag and drop the PCG assembly into the graph. To use the PCG assembly, let's add a copy points node to copy the level instance to the point we created earlier and connect the static mesh spawner. We'll need to set the mesh selector type to by attribute instead of weighted, and we'll need to add mesh for the attribute name. Everything appears to be working, and now we can set dress with this PCG graph in the same way as a level instance with the benefit of being able to build up procedural features in parallel with or after set dressing. Let's go another direction and try scattering some rocks on top of this landform mesh. I no longer want projection, so I'm going to clean up this section a bit. And I want to copy points again, but this time I'm going to use a mesh sampler for the source. And let's visualize what this looks like using our debug node. It's a bit hard to see anything, so let's change the scale method back to extents. Now let's randomize the point density before a transform node to achieve some random rotation and scale. We can do this with an attribute noise node with the input source set to density. I'll add a transform points node and add some random rotation on the local z-axis of each point. Now I want to add some noise to break up the uniform scattering. To do this, I'll add an attribute remap to control contrast of the attribute noise, and a spatial noise to create a purlin-like noise that'll get multiplied over the random noise for a varied look. And now I want to play around with the settings until I find a nice balance between the random noise and the spatial noise. Let's bring in a density filter to filter out some of the points using this mask we've created. We can make the rocks along the edges smaller than the center by adding an execute blueprint node and setting the blueprint element to scale by density. I want rocks to only show up on the up faces of the mesh. So let's add a normal to density node and play around with the settings a bit. Let's add a density filter and see what we get. I've added a static mesh spawner with all of the small rock meshes I want to use for this. It looks like we have a small issue where the transforms are misplaced, and it turns out I just had the wrong pin going into the copy points node. If we look closely at the rocks, it becomes apparent that a lot of the rocks are intersecting one another. We could use a bounds modifier with self-pruning to clean it up a bit, but I like an alternative method better. I'll create a graph parameter set to static mesh object reference, set it to an array, and then I'll add the small rock meshes to this parameter. After the density filter, I'll add a match and set attributes with our static meshes graph parameter plugged into mesh data. From there, I'll get the bounds from mesh, bounds modifier to adjust the scaling, and a self-pruning node. This will prevent intersections while doing so with the actual mesh dimensions rather than a cube. And just like we did previously, we'll need to change the static mesh spawner's mesh selector type to by attribute. I also like to copy the name of my graph parameter and paste it into the attribute name to prevent mismatch names. It looks like everything is working and it's ready for a bit of polish. After playing around with the scatter settings a bit, I found a balance of scatter that I like. Let's try making another set dressing tool with PCG. I've duplicated the graph we've been working out of, and I've also pruned some nodes out and left the core graph scattering functionality I want to keep for this next tool. Now we can select all of the nodes and collapse them into a single subgraph. This will help keep our main graph organized with a clean flow of data. Let's open the subgraph, and I'll start by selecting the input and changing the first pin name to points and setting the allowed type to points. This will act as the intake for the points we generate in the main graph. Now let's add another input pin called static meshes and set the allowed type to attribute set. And let's make sure that's plugged into our match and set attributes. Lastly, let's change the output pin name to points and set the allowed type to points. And this is what the subgraph looks like in our main graph now. Shifting gears a bit, let's make a blueprint actor and open it up. Let's add a spline and a PCG component. On the PCG component, we'll add our main PCG graph, and on the spline component, I want to enable closed loop. Now we can position the points wherever we want to have a good default size when dragging and dropping the actor into a scene. And this looks like a good size to me. Let's jump back into our main graph and search for the get spline data node. Similar to the get actor data node, this node is for sending data back and forth with splines in the scene. We can leave the get spline data node to its default settings, and let's add a spline sampler. In the spline sampler settings, let's set the dimension to on interior and set unbounded to true. I'll also increase the point density by decreasing the interior sample spacing value to 25. And it looks like we have points spawning on our spline in the scene. Next, let's go to our spline sampler and double click on the interior density falloff curve graph to open it in a new window. I find this most useful to create a gradient from the center of the spline to the outermost points, but you can create all kinds of curve effects such as concentric rings. Let's go back to our blueprint and add a few variables that we'll want to access in our PCG graph. I'll add an integer, name it density, and set the variable to public. I'll add another variable, name it static meshes, set it to a static mesh object reference, make it public, and I'll make the variable an array. I've set the density value to 25, which reflects what we had in our spline sampler, and I've assigned the rock meshes I want to use on my static mesh variable. Let's go back to the PCG graph and add a getActor property node. This will allow us to fetch the variable names we made in the blueprint, and if you spell the name incorrectly, you'll get an error. So let's add a property for static meshes with the same spelling as the blueprint variable, and plug that into our subgraph. And let's duplicate the getActor property node, set the property to density, and plug that into interior sample spacing on our spline sampler. Now I'll just test out the density setting on our blueprint in the scene to confirm that it's working. Back in the PCG graph, let's get our static meshes spawning. I'll take the spline sampler and route that into our PCG subgraph, and then I'll route the subgraph output to a static mesh spawner. Just like we've done a couple times before, we'll need to set the mesh selector type to by attribute, and we'll need to copy paste our actor property name. And we're seeing an error that's pretty common. Naming variables with spaces is usually a bit dicey and can cause a lot of naming conflicts like this. If we go back to the blueprint, replace the space in the static meshes variable with an underscore, and then replace the name in our getActor property and static mesh spawner, then our error will go away. In the interest of saving you all some time, I've skipped ahead a bit. Using the same techniques I've shown so far, we can expose additional parameters in the subgraph, add the variables to our blueprint, and add the relevant getActor properties needed. I've also added a scale by density after the spline to make meshes in the center bigger, and as it gets further away from the center, the rocks become smaller. The specific settings I'm using can be pulled directly from the final blueprint settings here. Now that we have a PCG scatter subgraph, I want to revisit the level instance assembly we first set up to build up some more procedural elements. This was the original setup minus the landscape projection we had, and I've done the basic setup we've done previously, including making the blueprint, variables, and getting actor property nodes. What we haven't covered is that I'm using world ray hit query to drive a surface sampler. In both ray hit query nodes, in the settings, ignore self hit must be disabled. We're also getting volume data on self in order to spawn points within a volume I've added to the blueprint. And this is the result. Let's talk performance and optimizations. For many projects at Quixel, we focus on cinematics, and this environment was set up to render the best quality possible. One way to start getting a better idea of our performance is by using viewport stats. Viewport stats can be accessed under the eye and viewport stats. I'll enable stat FPS and stat unit to get an idea of how the scene is running. Given that it's a cinematic scene, it's understandably struggling. Let's get a better idea of what our overhead is looking like by utilizing Unreal Insights. Running an Unreal Insights trace in Editor will capture the performance of the scene and the editor. So if you're planning to ship a project, it's best to run Unreal Insights in a packaged build or via launching in standalone game. To use Unreal Insights, we can select the Trace tab to access the options and settings. In our case, since I know I'm not CPU bound, I want to focus in on the GPU. So I'll go to Channels and untick the CPU. From there, I can select Start Trace from the menu, or I can use the small icon next to the dropdown. After a few seconds, I can stop the trace and then open the most recent trace. This tool has everything you'll need to profile performance in any project, and as a result it can feel a bit overwhelming if it's your first time using it. In this case, it'll be relatively easy to identify where the performance problems are coming from in this scene. In the top row, we can see a graph with spikes. This is our frame time graph where we can select individual frames and gather more information on what happened during that frame. There's also a nifty little guide here on the left that shows a visual for meeting FPS goals. To see more, we can select a frame we'd like to investigate, which will pull up more information including tracks and names. We don't need to look at the tracks, so we can bring our attention to the names. Names are color-coded, green being under a millisecond, orange being between a second and a millisecond, and red being over a second. Already, we're getting some pretty clear information that lighting and post-processing is taking up a lot of resources. And to dive deeper, we can select an option to see the callees. Again, we're seeing very high times to render lighting and post-processing, so let's go back to the scene and see what we can do to optimize. In the project settings, it looks like we're set to use Surface Cache for ray lighting mode and Global Tracing for software ray tracing mode, which are both the more performant options, and I want to keep everything else the same for right now. Many project settings can be overridden in the post-process volume, so I want to duplicate my original post-process volume, disable the old one, and start digging through the settings here. Bloom is set to convolution, which is more expensive, so I'm going to set that back to standard. Scrolling down, I want to see what global illumination and lumen reflection settings are applied. It looks like they've all been maxed out, so let's set these back to default and see if we can get comparable quality with these lower settings. And just by changing these settings, we're already seeing dramatically better performance from the scene without altering the visuals too much. Now that we've done some optimizations, let's go back to the trace dropdown. I'll enable Open Insights after trace, and I'll begin the trace. A cool feature with Unreal Insights is that you can set a region name, click Begin Region, and then End Region, and that will show up in tracks as a sort of chapter to help identify and organize performance checks. The key to optimizing any project is profiling, comparing the before and after, and repeating the process. Performance is looking quite a bit better with some easy wins, so let's shift gears and take a look at our viewport settings. If we select the speedometer-like button on the top right of the viewport, we'll see viewport scalability, material quality level, and screen percentage. Most games these days use some form of upscaling, and in our case, we're using temporal super resolution. So let's set up a custom override for screen percentage and set it to something lower, like 70%. And that helped us gain another 20 FPS. If we're still struggling with editor performance, we can always lower the viewport scalability as well, either in specific categories or across the board. If you want to have the most impact while still having higher quality in other areas, reference your trace and reduce project settings where performance is struggling. Thank you all for tuning in, and I hope you enjoyed. Don't forget, you can download the scene off of the Fab Marketplace, and I'll see you in the next one.